Good morning, everybody. I am your host, Peter Devine, and today our presentation is going to be on circular motion, and we're going to call this circular motion Part 1, because there will be a second part of this presentation. The first part of the presentation is merely to establish the direction of the acceleration of a body that is moving uniformly in a circle. And by uniformly, we mean it has a constant speed moving around in a circle. What we're going to do is we're going to refer to this speed at which this body, let's call it, there's the body. See, it's moving circularly around the circle. We're going to call the speed at which it moves v. And when we speak at the speed and the direction, we're going to put a little arrow on the top. So we have these two different ways of noting it. Now, in uniform circular motion, the speed itself taken at any particular point in the circle does not change. It's sort of a definition of that type of motion, and there are many different experiences we have of that type of motion, such as if you're on a merry-go-round and the merry-go-round has reached a constant velocity. That's a good example of circular motion, and there are many others. So this has a lot of practical applications. Now I'm going to assume that this little body moves around the circle, and here's the center of the circle, and this is the vertical direction in my diagram there. I'm going to also make a horizontal direction. What I want to do is find out what is the direction of the acceleration of this little body as it moves counterclockwise. What we're going to do is, at a certain time, which we'll just call t for the moment, you imagine it has moved to this position. And at any particular instant, the direction of the velocity, which we call v, the little thing, and we want to note its direction, is going to be on the tangent line, or the line absolutely perpendicular to the point where the body is and passing through the point where the body is. And for instance, at this point, the tangent line would go like that, and it's actually perpendicular there to the radius. So we want to establish that the direction of the velocity at any point, at any time, is the tangent line to going through the point at which our body is at. So now what I'd like to do is represent by a straight line, both in magnitude and direction, the velocity of this little particle, first at point A and then at point B. At point A, velocity is like that, and we'll even call it, why not, we'll call it A. And then at this point B, we notice that there's a little angle there here, so that angle is going to be the same as this angle here. And we're going to represent in magnitude and direction another line which has the same angle here. And we're going to call this v for the moment. Okay, that's our second velocity. Now, the lines of A and B are equal because the length of the lines represent the magnitude of the velocity, and the directions are, of course, represented by the directions of those two lines. Now, in order to get to B, in other words, if we have A and we wanted to add a velocity that would create exactly the velocity B, that velocity would simply be in magnitude and direction, represented by the line joining A and B at the endpoints of A and B. So, what I'd like to show is that this additional velocity, as the time gets smaller and smaller, is represented by a smaller and smaller line. But we're not so interested in the magnitude of that velocity. What we're really interested is in the direction. This is an equilateral triangle, meaning these two angles are equal. And we know that in a triangle, the sum of the angles of a triangle is 180 degrees. So let me just call this angle 1, angle 2, and angle 3. We know that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180 degrees. Okay. Now, as we get our time shorter and shorter, this angle is going to get smaller and smaller. And angle 3 here, angle 3 is going to get closer and closer to 0, whereas angle 1 and angle 2 are equal. So at the limit where they actually just start out their motion, angle 3 is virtually 0, whereas angle 1 plus angle 2 are equal to each other. So I can call that twice angle 2, for example, or twice angle 1, because angle 1 is really what I want to get. Twice 2 times the measure of angle 1, and twice the measure of angle 1 is now plus 0, is now 180 degrees, and at that point we'll divide both sides by 2, this being 0, and we end up getting the measure of angle 1 at the very start of the motion is 90 degrees, which is exactly straight down to the center. Now, so therefore we can say at the beginning of the motion, the direction of the velocity being generated in order to turn this into a curved circle rather than just going straight. The direction of that additional velocity, this additional velocity here, is going to be straight down in this diagram, which means straight through the center of the diagram. It is directed towards the center. And if we were to draw another point, say this point, and carry out the same calculation or the same investigation, we would also find that it's exactly the same. In other words, had we shifted that up, it would still be through the center. In fact, because of symmetry, because our circumstances really don't change as the circle turns, any point will give us the same direction, which is going to be through the center of the circle. Furthermore, since this is always uniformly circulating around, and there's no difference between any particular point we choose, the magnitude of the acceleration is going to be also the same, even though we don't know exactly what it is, but it's not going to change because the circumstances do not change on the circle. So we've established two things in this short presentation. One, that the direction of the acceleration is toward the center of the circle. And two, the magnitude of the acceleration is uniform. Now, in part two, we're going to find out exactly how much that acceleration is the magnitude of the acceleration in terms of the velocity of this body going around the circle and in terms of the radius of the circle, which are the two main factors that regulate the acceleration. So, thank you very much for listening.